My name is Joe Davison. I'm a research engineer at a company in New York and Paris. It's a startup, probably 20 to 30 people, called Hugging Face. And what we really do is open source natural language processing technology. Our goal is to be as open as possible in taking the technology that is being developed by the research community and by big players in natural language processing. So if you've heard of models like BERT, that's what we'll talk about a little bit today. And really, we just want to make it as accessible as possible for anyone to be able to access and use this technology. So a little about me. My name is Joe Davison. As I said, you can follow me at JOEDDAV on Twitter. My background is I did my undergraduate degree in computer science. And while that, I was at a university called Brigham Young University. While I was doing that, I got interested in machine learning. This was kind of the early days of when deep learning was starting to take off a little bit. So there was a lot of excitement and buzz around it. And I was fortunate enough to take some classes and work with some people that were really interested in getting into this. And so I kind of jumped into it full-throatedly. After that, I went to Harvard, where I did my master's degree in data science. And there I started to focus in a little bit more on natural language processing, which is one of the common applications of machine learning, and especially deep learning and the types of machine learning techniques that have developed in recent years, as I'll talk about here. So first, I just want to dive in by talking about NLP and ask, what is natural language processing? The term is relatively self-explanatory at a glance. When we talk about natural language processing, one simple explanation is you're just trying to process natural human language. If you have some text input that is text that came from a human speaker just speaking as they would to another human being, what can we do with that? What kind of insight can we extract from that? And how can we, oops, click the link in the chat and it messed up. Sorry about that. How can we extract valuable information from data? How can we understand a human's intention, a human's the sentiment behind a human speech, or how can we generate text to communicate with a human in the case of like chatbots and natural language generation? These all fall under the kind of broad umbrella of natural language processing. And I'll also note that computational linguistics is another term that is kind of used alongside natural language processing a little bit. You could quibble about the differences, but in many cases there is overlap, if not that they're just synonymous. So just as an example of a kind of natural language processing task that might be useful, let's consider this one. This is called sentiment analysis or sentiment classification. And here we have two short one-sentence reviews from Yelp. So the first is pretty positive. It's awesome drink specials. There's keywords like fantastic, delicious. And then the second one is more negative. It's another restaurant. They were very disappointed in the customer service. We ordered Reubens and wanted coleslaw instead of kraut. And as the goal of sentiment classification is to take text, somehow put it into the computer in a way that the machine can represent it, and then get the computer to spit out that this was a positive review. Or conversely, in the second example, what we might want to do is take the text, again, process it, put it into machine readable format, and get the computer to predict, oh, this is a negative review. So you can see that if you knew nothing about natural language processing and you just saw this task, you might be able to start teasing out some code for how you could do this. You could identify some positive words like fantastic and awesome that if they occurred within a string, you could say the review is positive, and likewise with negative reviews. And you can actually do that, and people have done that in simple examples like this for things like sentiment classification. And it works okay, but it turns out that that's not always the most effective approach that you can take, as you might imagine. There are lots of cases when you would have a positive word occurring in a statement that is in fact negative, and vice versa. So let me show one more example of another kind of NLP task that's a little bit harder. And then I'll talk a little bit about methods. So, oops, that's supposed to be hidden. Oh, well, I'll just show the whole slide. So this is an example called automatic summarization. Specifically, it's extractive summarization. And what we have on the left is a passage from a book, and it's talking about this particular thing relating to architecture, and it's not really that important. The point is there's a passage, and the task that the machine has to do is take this passage called the context and take this question, which in our case is what is in front of the Notre Dame main building, and it has to identify an answer. Okay, in this case, a copper statue of Christ. Oh, I'm sorry, I mislabeled this. This is not automatic summarization. This is question answering. I was originally going to put a summarization example, and I decided on question answering instead. So that should say question answering at the top. I apologize. So in this case, there are lots of different forms of question answering. In this one, the task is to point to the span in the original context that contains the answer to the question below. So you can see this case is a little bit more challenging. If I were to ask a really savvy programmer to sit down and figure out a way to do this, to answer arbitrary questions by pointing to the answer in a long passage of text, it would be much less trivial than in the previous example, where we could do pretty well by just identifying keywords or simple patterns that might be indicative of one class or the other. Excuse me. So this leads to the point that when it comes to natural language processing with a lot of these tasks, handcrafted rules only get you so far. And instead, what we can do is use algorithms that are specifically designed to discover rules from data. So instead of trying to craft rules in the previous example that would conform to our intuitions, we can just gather a whole bunch of examples of question, context, answer data that we could then give to a machine learning algorithm so that it can uncover the statistical patterns that are in that data set to predict the correct answer. So all of this is to say is, as I said in the XKCD example, you basically pour a pile of data onto this big algorithm, often powered by linear algebra, and then stir it around until the pile looks right. And that's a very crass way of saying it. It's not exactly accurate. There's a lot more math and theory to it than that, but that's the general idea. And probably most of you are familiar with the concept of machine learning, but just to go over the concept, that's what we're trying to do, is we're trying to take a whole bunch of examples like the one here and get some model to infer the patterns in the text that can help it predict the correct answer without relying on deterministic handcrafted rules. Okay. So we've been doing this in NLP for a long time. Statistical learning has been around for some time, and it has, for quite a while, even been the predominantly most successful application to lots of NLP tasks, especially more challenging NLP tasks. But we took a big turn in around 2017, 2018 with the advent of the transformer architecture, and of BERT. So what you basically have is a confluence of a huge increase in computational power, and specifically the thing that has helped us a lot is GPU technology and the ability to parallelize linear computations like linear algebra. So that development has been really important. Another one is we have a lot more data now, and the reason for that isn't particularly surprising. It's that we have the internet. And there is so much text on the internet that it created an opportunity to try to get really clever about how we can use the data that naturally finds itself on the internet to try to learn better models, okay? So those two things, compute power and large text data sets, were really important. And then we also we made a few innovations in the machine learning side of things. We figured out some particular types of machine learning architectures, specific types of neural networks called transformers, which are really effective at modeling long sequences, which is what a piece of text is. It's a whole bunch of words separated by time in some sense. So we got really good at this, and that's the box down here, self-supervised training and transfer learning. So let me describe that a little bit more. BERT is the name of the most popular, or I guess arguably the model which kicked off this kind of boom in transfer learning in NLP. And it was based off of the transformer architecture. It wasn't the first transformer architecture, but it was the first one that utilized a whole sequence, a whole piece of text when making predictions about any subpart of the text. So let me describe how this works a little bit. For now, BERT is just going to be a black box. That is, we're not going to worry too much about the inner workings. I'm just going to represent it by this cute little BERT figure. And all you really need to know is that BERT takes in a span of text and can output something. So that could be another span of text. It could be a single digit or a scalar. It could be anything really. So BERT takes in a span of text and has tons and tons of knobs that are turned, these parameters that are turned so that it can perform well at a particular task. So what we do is we have two stages. We have the pre-training, and in a second I'll describe the fine-tuning stage here. So in the pre-training stage, this is where we really take advantage of the massive amount of text that we have on the internet, like I mentioned. In a standard machine learning paradigm, you have a machine learning model, so that's BERT in this case, and you want to map some set of inputs to outputs. So in like the sentiment case up here, you might take in these different reviews, and the outputs would be whether they're positive or negative. And you would train a machine learning model to learn the patterns that allowed it to know whether it was positive or negative based off of the massive amount of data it have. And when you have enough data, it's able to just learn those patterns from experience without needing any fundamental reasoning or world experience or knowledge to tell it what those words really mean. It can just learn the patterns that help it to be successful. In this paradigm, what we're doing is we start with a pre-training task. The pre-training stage, what we do is we take an enormous amount of what we would call unlabeled text. So this is text. It doesn't have a positive or negative label or anything that tells us something structural about the text. It's just raw text. So we take that text, and the task that we're giving to BERT, our model, is we take a span of text. So this is the beginning of the first sentence from the Wikipedia page on Barack Obama. Okay, so it's just a raw piece of text. So we take this span. Barack Hussein Obama II is a mask, politician, and attorney. And so as you can see, what we've done here is we've obscured one of the words. And in this case, the word is American. He is an American politician and attorney. But we tools to get it to go in the right direction of learning how to predict the text. The reason we do this is because when you do this on an enormous amount of text, and in the case of BERT, they actually did it on all of Wikipedia and on a whole bunch of books. So they just took like tons and tons of text from books and all of Wikipedia and trained BERT to predict these hidden words 1,000 times over, okay? And when you do this, it turns out that BERT is actually able to learn some really useful and generic linguistic, quote unquote, knowledge. It's able to learn to associate, for example, that Barack Obama is correlated with American, right? And that if it sees Barack Obama, politician and attorney, that likely means that the word that's to be filled in there is American. And it can likewise do the same if it was talking about a French politician, right? It would learn to fill in French. So it's learning all of these really complex associations between different types of words that appear in sentences in different ways together, okay? That's really abstract, but basically what we've done here is in the pre-training stage, we've given BERT a core way to extract useful information about text that can be used in all kinds of stuff down the line, okay? So then what we do is, now what we can say, okay, now that I've trained BERT on this pre-training task, what I really want to do is what we call fine-tuning it, or to transfer learn it on the specific thing that I'm interested in. And that is to get BERT to predict whether Yelp reviews are positive or negative. And when you've done this pre-training stage, the model is able to capture and understand a lot, significantly more information before it even sees a single Yelp example than would otherwise be possible. So when it starts to see this Yelp data, it has somewhere to start. It already understands a little bit, or has a little bit of ability to extract information about the sentences that are being passed to the model. And then after that, it takes a lot less data and you get a lot better performance training BERT on this sentiment classification task than if you were to just train a machine learning model from scratch without doing the pre-training step, okay? And the really powerful thing, the reason that BERT made waves and sort of became this new paradigm of doing machine learning and NLP, is because when you do this, you get state-of-the-art performance on a whole variety of NLP tasks that are trying to probe what a machine learning model does and does not understand about the text that it's processing, okay? So it kind of blew away the benchmarks, and in many cases, it was able to surpass these benchmarks on these specific tasks, even without having as much data as would have otherwise been required. So it can get better results with less data. So this is super powerful, and all kinds of people, when this started to emerge as a really clear and powerful machine learning technique, started to realize that this would be really useful, and it attracted a lot of attention both in the research community as well as in industry. People started to realize that this was a good way to get performance on a lot of different types of natural language tasks that they were interested in doing for their business or for their research. So shortly after BERT came along, Hugging Face developed a tool open source tool called, at the time, PyTorch pre-trained BERT. And it was just a GitHub project that was a port of the original BERT code that had been released by Google. BERT was developed by Google researchers, if I didn't mention that. And the idea was to make it really easy to take a model that had already been pre-trained on Wikipedia and on this books corpus and everything. So you already have the pre-training step done, and now you can just fine-tune it on your data set. And that is something that is computationally feasible enough that it can be done by regular practitioners without access to huge technical teams and huge computational budgets. The pre-training step requires a lot of compute. Fine-tuning is actually really easy to do with not too much compute. So this tool was designed to download all these different versions of BERT that Google had released, the different sizes of the model and so forth, and make it really easy to use on anything and to fine-tune on a specific task. Since then, and even prior to then, a variety of other transformer models had been released with their own pre-trained weights released for people to fine-tune. And these have found their way into the library as well. So now it's simply called transformers. We also removed PyTorch from the name. PyTorch is one of the most popular deep learning frameworks, if you're unfamiliar. The other kind of really popular one is TensorFlow, and then there are some others. Transformers library now supports PyTorch and TensorFlow. So we have support for multiple different backends. And it houses a whole bunch of different models that have been pre-trained, including BERT, GPT-2, XLNet, T5. There are a whole bunch of them. And actually now even hosts a community model hub where people can upload the weights that they have trained on their specific task. So you not only have access to models that have been pre-trained on Wikipedia, but you also have access to data sets or to models that have been fine-tuned on Yelp, or models that have been fine-tuned on Squad, which is a question answering data set. And obviously, if you have your own data set, you may still want to fine-tune it on your own data set, but the model hub that Hugging Face hosts now has, I believe, somewhere around 3,000 different models that have been uploaded by people with functionality ranging from translation to sentiment classification to all kinds of stuff that you might want to do, and it's all accessible with this within this really simple interface. So that's really where we're focused. The goal of Hugging Face is to make these tools as accessible as possible, to make these models as accessible as possible, and to do it in an open way. And I think that's kind of the exciting thing about Software Freedom Day, is the emphasis that we really share with our vision of doing things in a way that is open and transparent. So not only can the community benefit from the work that the tools that we produce, but also, more importantly even, is that we benefit from the community's contributions. The Transformers library has over 300 contributors, really great community of people that help us to make the tools as useful as possible. And on top of the contributors to the actual repo, we obviously have people that download and trade models and upload models to our model hub and share those resources with the community. In addition to just the code, we believe in the importance of actually sharing models that can then be used for all kinds of different tasks and settings, despite the fact that most people wouldn't have the computational resources to train these kinds of models from scratch. So real quick, I'd like to just show you a little bit actually of how the library can be used. So I've opened here a notebook in Google Colab, which, if you're familiar, is just a kind of interactive coding environment that is useful for demos like this. And so we installed the Transformers library here. And then all I've done so far is I've imported two modules. I've imported, or two classes, BERT for masked language modeling and BERT Tokenizer. Okay. And then actually downloading and using the pre-trained weights is as easy as calling this from pre-trained class method, where I specify the identifier. This is just a identifier that points to our S3 bucket and says, give me the weights for this version of BERT that you have in your model hub. Okay, so we run that, and that's it. We now have BERT sitting in our library, and we can start to do useful stuff for it. So let's do an example where we take a sentence here. We can do kind of something similar to the example we were doing. Barack Obama is a, and then I'm going to use a special mask token, mask politician. Is a mask politician and lawyer, I think. And so we'll say this is our sentence. And with NLP models, the first thing you have to do is you can't really do machine learning on raw text very easily. So you have to do something called tokenization, which is basically where you just take this sentence and turn it into a list of numerical representations. So in our library, we, in addition to include the tokenization process, is really tightly linked with the modeling process. They kind of go hand in hand. So we also provide the tokenizers for each of the models that we provide. So that's why I loaded that up here in addition to the model above. So just to see how this works, I could call tokenizer.encode sentence, and you get a list of numbers. And what these numbers are is they're literally just indices that map words to indices, so that they can be fed in and dealt with by a mathematical machine learning model. And you'll see I can kind of I can decode this encoding and get the original sentence back. And the CLS and SEP token, SEP at the end, are just additional special tokens that BERT uses to understand the sequences it's taking in. So let's take, so I'm gonna say we want to get all of the input features that we might need to feed this sentence into BERT. So I'll call that encodings. And I can also just call this tokenizer with the call method and pass it the text. And there are a whole bunch of options it gives you to get the right kind of tokenization that you want. I won't go into those details. I'm just going to pass one argument here that just says I want you to return the encodings as PyTorch tensors instead of as Python lists, since our model is in PyTorch. Now, if you see encodings gives me a few different things. These are just the different types of inputs that BERT takes in. So the input IDs is the indices that I talked to you about, and then there's an attention mask, and I don't need to get into details of what those are, but this is all we need to actually call our model and just pass these encodings as keyword arguments. Now, what you're seeing here is the logic. So maybe if I print out the shape, it'll help give you some intuition of what's happening here. The shape of the output here is, one is just the batch size. So we have only passed one sentence into the model. 13 is the number of tokens that were fed in the model. So after we tokenized it, you have 13 individual like words. You can think of those words that are a little different, but basically the same thing. And then this is 30,522 is the number of words in our vocabulary. So what we have is the 0th sentence, the 0th token, I'll do the 1th token, and the log probability of the kth word, where so I can do 100, and that's the log probability according to our machine learning model that the output at that sequence is the token corresponding to the index 100. Sorry, that's kind of confusing. The point here, what we can do with this is we can take the output for the mask token So let's see which one that is. Input IDs. Yeah, so 103 is the mask token. So right there, we can just do so all I'm doing is I'm getting the position that the mask token sits in. So mask position equals that. 103 is not in list. What did I do wrong? Probably, there we go. Yeah, so it's in the 5th position. So now if I take the, we call them the logits from the model, which is the probabilities of the different tokens, like I said, and then print out the shape of that. And then I want to say for our sentence here, in the mask position, so in the 5th position there, what is the token with the highest probability? Okay, and it says it's token with the index 2137. So we can literally now just feed that back into our tokenizer. Or I'll do convert tokens. Sorry, one second here. Coding lab is a little stressful sometimes. American, okay. So that's kind of confusing, but let me just walk over what just happened again. So we took sentence and we masked the American token so that we could see if our model was capable of predicting that that was the missing token, right? Because that's the task that it was pre-trained to do. We tokenize it and get it ready to be fed into the model. And then I just kept track of the position in the sequence where the mask token sits, so that after I get the outputs from the model, I can index to that position, the mask position, and find the value of the token with the highest probability. Okay, so that is American. That's the low level. We also have some tools built in to make it easy to do this, though. So let me show you. This is called our pipeline. So we have one built in that's made specifically for doing this, called fill mask, the fill mask pipeline. And I can actually just pass the model that we just created. And instead of doing all of that work manually of tokenizing stuff, I can just pass in our sentence. And it will return the most likely predictions with their corresponding probabilities. So kind of does the work for you for this particular task. So the cool thing is this just shows that you can load in this model among many, many different types of machine learning models and instantly access them as PyTorch models. So if you were wanting to fine tune this further, you could do a backwards pass as you normally would in PyTorch. And if you're familiar with PyTorch, this is going to be a little more comprehensible than what I mean. But the point is that it's very simple to fine tune this on a particular task. So let me show you briefly how this relates to our model hub. So on our website here at huggingface.co/models, we have a huge collection of models that have been uploaded both by community contributors and by the Hugging Face team from the original, from weights that have been released from original research models. So here we have like the example, you see BERT based uncased is the one that we just used. And we can click on it, see all kinds of useful information about it, the number of downloads, this one gets quite a few, as well as a description of the model and a snippet of how it can be used, which is just like what I just showed you. We also have some live serving built in right here. So if you ever want to play with a model, you can actually just play with it right here in the hub, and it'll show you. So we can do Barack Obama is on blank politician and lawyer, and just right here. You can get the outputs and play with different types of models. But that's just the ability to fill masking. You might be thinking like, okay, but yeah, how is it that useful for me to be able to just predict a missing word in a sequence? And that gets back a little bit to when I was talking about the pre-training fine-tuning paradigm. The pre-training task was to fill the missing word, the masked word. The fine-tuning task can be whatever you want. The reason it can be whatever you want is because the version of the model that I showed you here above was a very particular version, which it has a particular type of output layer, and that output layer predicts the missing words. So what we can do instead is get the layer before it. And in the context of deep learning, that's a powerful thing to do, as you're probably familiar, because if you chop off the last layer of a neural network, what you get is an intermediate layer that is basically a really good, a really like powerful representation of the data. So if I pass in our sentence, Barack Obama is an American lawyer and politician, the second to last layer of BERT would be a latent numerical representation of that sentence that's really useful and powerful. And in the case of transformers like BERT, it's actually a representation of every single word in that sequence as well. The reason that's useful is because after you chop off that layer, then you can add an additional layer however you want to. And that's when you can fine tune it specifically to your task. So actually what I can do here is I'll do BERT for sequence classification. And what that means is that it's just BERT as usual, but with an additional layer at the very end that is a classification layer. And so I can go BERT for sequence classification here. And say I want a sequence classifier with 2 labels in the output layer. Now what's happening here is, and you'll get a warning to what I was just about to say, is that it's giving me this warning that some weights of the model checkpoints, BERT based on case, were not used when initializing. And it lists the names of these different layers. These layers correspond to the classification layer that I just mentioned. So we have the base BERT model, which you call the encoder, and that's all pre-trained. And so when I call from pre-trained, that entire network up until the last layer is loaded from a pre-trained model with super useful information already there. The last layer, the final layer, is then the classification layer, and that is completely random, which means that we can tune it to whatever task we want. So like the Yelp sentiment classification example. And you'll see if I print the model output, the summary of the model, you have this final classification layer. Easy to just on a particular classification task. However, there are also models in the hub that have been fine-tuned on classification in addition to just the pre-training task. So I can, let's find an example of this. So let's say like sentiment, let's see, Which one do I want to use? Yeah, so here, fine-tuned SS2. This is a version of Distilbert, which has been trained on a particular task. Although, let me find a BERT example, sorry. Let's see if there's a BERT base that is kind of what I'm interested in. So I'm not sure if that's clear, but the general idea there is that you can, here, let me actually show you with pipelines. That's the right way to go about this. Okay, so what I want to show you here is general pre-trained models in the Hugging Face Model Hub. So I can call our pipeline as I did before, and let's just say I want to do I think it's sentence classification. Sentiment analysis, okay. Sentiment analysis is one of the pre-trained tasks we have in here. So if I just put in that I want a sentiment analysis pipeline, it has a default configuration for the model that it should use from the model hub. And it automatically downloads the model and the tokenizer and builds all that stuff in so that as soon as it's loaded, I can putting in sentences and getting labels out. So I hated this movie. And I should see a negative sentiment, and I do. Great. I really liked this movie. Label positive. Okay, great. So this is a particular case where not only do we have BERT on the pre-training task that's already loaded, but we can also load in the weights for the particular task, and the whole model will be trained from top to bottom for the particular task. And you can also see what that is. So like NLP is the pipeline object, but we can access the model that's being used. So you can see it's a Distilbert for sequence classification model, and we can access that directly. We can fine tune it. We can do whatever we'd like with it. Okay, great. And then just really quickly, that's kind of an overview of our model hub. While I'm here, I just wanted to also plug that we also have a datasets library that we've introduced relatively recently. And even some non-text datasets that are all easily accessible and downloadable. So I can, I talked about our Yelp dataset. I can look at this Yelp polarity dataset. Here's the code to download that dataset with our library. Here's a citation for the original paper the dataset come from, a description. And we also have this handy Browse NLP Viewer button where I can click that and it'll actually open an interactive browser where, and again, I have the description and everything, but then I can actually just browse the data sets and look at the different examples and their labels. Over here on the left, you'll see I can do that for any data set that's in our library. So this is just a really useful thing. We have so many data sets that are all accessible in one place through the same API, but also because you can literally just click a few buttons on our website and you can be looking at all of them. So yeah, like another, let's say I want to do Squad. Squad is a question answering data set like we talked about. So here you have the, oh, I clicked the wrong one. I was confused why the format was wrong. So here, yeah, you have a number, you have the context, like we mentioned, that's the passage that you have to answer the question about, and then the question, and then the JSON format of the answer, its position, and the substring that is the answer to the question pointed here. So I would just recommend looking at this if you're interested in NLP and machine learning. I think this is kind of a useful place to browse different data sets and get a feel for what you're doing when you're working on a given project. So lastly, I just wanted to show really briefly the library itself. This is our GitHub repo. For those of you that are interested in contributing to a project like this, we love contributors. Would love to have you. It's probably it would probably be useful if you had a relatively strong understanding of NLP models, in particular transformers like BERT, and that you had a strong foundation or a relatively strong foundation, at least in either PyTorch or TensorFlow, which are the common libraries. But it's an incredibly fast-moving library. New research is being done all the time. It's pretty common for us to see, you know, a paper drop that a new kind of NLP model was trained, and so the authors will write a paper about it, and they'll release the weights, and it's not uncommon for us to almost immediately after that start working on porting it and putting it into our library. So it moves pretty quickly. There's a good first issue here label, which is just a good thing to know about in open source in general. A lot of repositories have this, where sometimes the dataset maintainers will add this tag to things that are good for someone that is just trying to get up on their feet. Yeah, so that would be a good place to start if you have a relatively strong foundation in transformer models and are interested in contributing to the library. So yeah, I hope that was helpful. I know some of that was a little kind of rambly tour showing you around, but I kind of wanted to just give you a hands-on feel for what it actually feels like using the library. Yeah, that's all I have. I would if you have them here or ask them on Zoom, I would love to hear them.
Yeah, thank you, Joe, for the wonderful talk. So first of all, I have one question for you, and I'm asking that on behalf of many participants here. So would you suggest using Hugging Face at the start if anyone is starting to learn NLP, or would you say to them to learn the basics of models like transformers or BERT, and then code using Python, TensorFlow, and PyTorch, and then go on using Hugging Face? Or would you suggest them to directly use Hugging Face?
Yeah, it's a good question. So let me answer that in two parts. The first part is that there's more. So Hugging Face's library transformers is specifically focused on this one new architecture called transformers, which is, again, like I talked about, the pre-training fine-tuning paradigm. If you're interested in using those types of models, if you're interested in using BERT or GPT-2 or AccelNet or T5, if you're interested in using one of those models, either just because it's pre-trained or because you want to fine-tune it on a task, then absolutely use our library transformers. I really think it's the easiest way to access them, and you also have the convenience of easily being able to switch between different models pretty trivially. So that said, I think for someone just starting to learn NLP, transformers are one useful and very recent and powerful tool in the toolkit, but they're not the only tool in the toolkit. So it's useful to understand machine learning in general, like, first of all, machine learning, what a machine learning model does, what it means to optimize a loss function, what it means to do inference, some of these kinds of machine learning fundamentals. And then maybe some also more traditional NLP fundamentals, like what it means to tokenize a sentence and what word embeddings are, what embeddings are in general. But I think once you have a few of these kind of foundational pieces, diving into transformers using our library is going to be a pretty fun way to go. Some people would say it's overkill because their models are so big and beefy and powerful for someone just learning. But I think it's actually kind of good because using the kind of recent state-of-the-art stuff is fun. Like when I first got into machine learning, I was using Keras and I was using pre-trained models, and it was all very high level. Like I didn't have a very deep understanding of what I was doing at the time. But I think the fact that I was able to figure out how to do it, even as poor as my understanding was at the time, helped me to stay interested and to really enjoy the process of trying machine learning models out on different types of tasks. So I think read up on some basic fundamentals of like machine learning and natural language processing, and then maybe make sure, like read a blog post on BERT or something to like make sure you understand what BERT is and how it works a little bit. And then absolutely dive into transformers, try fine tuning it on a model on something that you think would be a cool task, or there's all kinds of fun stuff you can do with it.
Yeah, okay. So we have one question in the Q&A. So the question is from Archit. How will you differentiate between BERT and GPT-3 model?
Yeah, so the biggest difference between BERT and GPT-3 is a distinction called bidirectional versus unidirectional models or classical language models. So here's what I mean by that. Let me pull up one of these again. Where's the one where yeah, right here. So like in the case of BERT, BERT is trained to take this whole text and predict the value of the missing mask token, right? That's what we talked about. And so it does, and when it does that, it can see all of these other words. It knows everything except for the position of this. That's what BERT does. GPT, GPT-2, GPT-3, all of these models are unidirectional, which means they only look at the words that come before the token that they're trying to predict. The reason that they do it that way is partly because it's a little faster to do the pre-training, I think. And also because there's kind of academic reasons to it too. Like there's a notion of a formal language model, which is like this very formal, like kind of academic concept. And the left to right model is the biggest distinguishing factor of that. Okay, so that's one reason. And that's also why BERT does a lot better than just left to right models on a lot of tasks when you're fine tuning, because you can imagine in a lot of cases it's useful to know both about the left side of a sentence and the right side of a sentence, not just the left side of a sentence. Okay, so that's one important distinction. The other is just specifically with respect to GPT-3, that GPT-3 is really huge in the sense that like the number of parameters that you're actually tuning when you're doing the pre-training is really, really, really big. And what GPT-3, the people at OpenAI did with GPT-3 is they showed that when these models get bigger and bigger, they do better and better, even if the amount of data they're trained on is pretty much the same. And so that's a really interesting finding. I think one of the things we're really concerned about at Hugging Face is making sure that we're not going overkill and with the size of models and making them too big and cumbersome. GPT-3, for example, if you or I had access to their weights of a GPT-3 model, which we don't, but if we did, it would take significant expertise to even figure out how to load that model onto a machine, because it uses so much memory that the amount of RAM you would need is crazy, and you would have to distribute it across the model across. It's pretty practical. It's pretty feasible for most anyone to use. There are methods for making pre-trained machine learning models smaller. So, and we actually do a lot of that at Hugging Face. We're actually involved with a competition that is all about making models smaller and more efficient, which we believe is important, not only to make the models more accessible, but also is good for the environment and all kinds of stuff like that. So that's a little rambly, but short answer is GPT-3 is so large that it's kind of impractical to use unless you have like a lot of computational resources and technical expertise, whereas BERT is much smaller and more practical for people like you to use. And also, OpenAI hasn't released GPT-3's weights, so we can't really use it except through their paid API, whereas BERT has been released, and lots of models like BERT have been released, and we can use them for free.
Okay, great. So we have one question from Archit again. So Archit, you can unmute yourself and ask the question.
Hi, Joe. Am I audible?
Yes.
Yeah.
Okay, so I have a question that I have been doing machine learning for a year now. So I was hoping to get into the field of research. So what's the first step that a student should take, like at the bachelor's level?
To get into research?
Yeah.
That's a good question. It depends a lot on the individual person and where you're going to school. Do you know if you have faculty members there, anyone you've taken classes with that does the kind of research you're interested in?
Yeah, we have faculty members that do similar research that I'm interested in. So I'm in contact with them, but the difference in level is very different. As I see, the research paper I read, they are a lot more informative than what the research that our faculty is doing. So how can we cope up with the difference? I'm not getting it.
Yeah, I mean, it's a tough question. Can you elaborate what you mean at the end a little more? I think you cut out for a second. With you said the
Pardon?
papers were more informative.
Can you please pardon? I didn't get it. No.
You said something about the papers having more detail or something.
Yeah.
I just missed what you said there.
Yeah. So what I was saying that is I read papers from University of California and Stanford. So the research they are doing is more mathematically oriented. They are developing models based on mathematics. But what our faculty is doing is trying to get a better algorithm somewhere. The strategies are totally different. You get that?
Yeah. No, I get it. It's tough. It's definitely a hard thing to break into, especially when as an undergrad, I think. And to be honest, I don't really know the right answer. I think the best thing you can do is try to find people that can kind of mentor you and help you. And it sounds like you have some faculty members there. If you could work with them on a project, even if it's small scale, even if it's a stepping stone to where you want to be in the future, then that's a good thing, and that will be helpful. The research is tough. We'll pretend it's not tough. And I will say, with regards to the mathematicalness of papers that you read and are being published, it does depend a little bit on the field. So I think if you read like some more NLP specific papers, they tend to be less math heavy and a little bit more focused on trying to understand model behavior and kind of design the right kind of behavior to get models to do the things we want. Yeah, feel free to shoot me an email and I can try to try to answer your question a little bit.
Can you tell us about some open source organizations like who are doing research and all that stuff? That would be a great help. Like Hugging Face is one of them, but other than that, if someone else.
Yeah, well, I mean, the big guys are doing research and open source. So like Facebook does a lot of open source and they do a lot of research. Same with Google. And there's OpenAI, who we've talked about with GPT-3. They definitely do. They do research. I guess I shouldn't say that they do research in open source. They kind of do research. They publish their findings sometimes, but they don't seem to really be open sourcing much these days. But there are a bunch of them. There's AI, which is a really good NLP group. Salesforce has a good NLP research arm. There's a number of them.
Okay. So thank you for that.
Okay, so we can take one last question maybe. What's the latest research in the field of NLP after transformers GPT models? In what direction we are actually going?
Yeah, that's a good question. I think the unsatisfying answer is we don't really know yet. We're still kind of, transformers are still pretty new, only a few years old. It's pretty young in a research setting. So one big direction is trying to figure out a way to make models that are as powerful as the really big ones, but without having to make them be so big. So there are a whole bunch of people that are working on stuff like distillation is a common research area, and pruning, and both of these basically involve taking a big pre-trained model and kind of transferring its capabilities to a much smaller model after the fact. And that works pretty well, actually, a lot of the time. But it still is tough when you have such enormous models that are so complex to get them to the level that they'll really be practical. And then we also would like to be able to make them smaller before distilling them, right? Like we would like to train smaller models too. Training really big models takes a ton of compute and a ton of money. The OpenAI, when they trained the model GPT-3, must have spent in the tens of millions of dollars just for the computational resources to train their model. And they're probably spending tens of millions more hosting it and letting people use it. So making these models smaller is a really big one. Another one that's a lot of people are interested in right now is cross-lingual abilities. So getting models that work in all kinds of languages and especially can learn to perform well on low resource languages without much data, because that's a big problem. There are, a ton of languages out there that don't have enough resources to train really big beefy models. So trying to figure out ways that we
Okay.
I think I just cut out or something, my internet. Anyway, sorry, I was just wrapping up. I was just saying, another one is zero or few shot learning, where you want to train a model to do a particular task, but you don't have the data to do it. There are lots of creative ways that people come up with of training a model on one task and then getting it to work on a similar task without any data on that one, and all kinds of stuff like that. So that's another area that I personally think is interesting and exciting.
Okay, great, Joe. Thank you for the wonderful talk. If we would have any questions later on, we can take it on Slack channel. I've shared the link of the Slack. So thank you, Joe, for the wonderful talk.
Yeah, thank you for having me.